For a series a sub n to converge, the n term a sub n must satisfy that a sub n approaches 0 and n approaches infinity. So therefore, from the algebraic limit property of sequence, the limit at k approaches infinity of a sub k equal to the limit at k approaches infinity of the sum of s sub k minus s of sub k minus 1. And we can split the limit. Let's say this limit at k approaches infinity of s sub k minus the limit at k approaches infinity of s sub k minus 1 is equal s minus s equal to 0. So therefore, the series is converged. If the series converge, the nth term a sub n approaches 0 as n approaches infinity. Is an important consequence of this fact is that if a sub n does not approach 0 at n approaches infinity, then the series diverge. So here we have a theorem, the divergence test. The limit at n approaches infinity of a sub n equal to a number c that is not 0 of the limit at n approaches infinity, then or the limit at n approaches infinity does not exist, this is an or, then the series diverge. Note that if the limit at n approaches infinity to a sub n equal to 0, then the divergence test is inconclusive, which means we can't say anything about whether the series actually converge or diverge. Let's take a look at the integral test. Consider the series, the sum of as n equal 1 to infinity, the 1 over n squared equal to, and this is equal to 1 plus 1 4 plus 1 9 plus 1 over 16, so on and so forth. There is no simple formula for the sum of the first n term, but I was using Excel and I able to estimate the sum to be 1.64 at n approaches infinity. So it looked like the series is convergent. And let's go ahead and compare. Let's go ahead and verify this with a graph. So this curve here is the curve y equal to 1 over x squared. And the sum of the n term as n approaches infinity is just the area under this curve, right? So let's divide this out. So here we have the area. So here's 1, here's the first term. So here we have 1/4. So here 1/2 square, 1/3 square, so on and so forth. So it looks like I can estimate the sum of the series by using the integral, calculate the area under the curve, right? So what I can do here is I can estimate this by calculate the integral. Here I know that if I can't make it from 0 to infinity, okay, of 1 over x squared dx, because at x equals 0, we have this function does not define. But I do know that the first part of the area equal 1, so this is just equal 1 plus the integral from 1 to infinity, the 1 over x squared dx. I can evaluate that integral by using improper integral, if you remember. So this is 1 plus the limit at b approaches infinity of integral from 1 to b of 1 over x squared dx. That is 1 plus the limit at b approaches infinity of 1 over x negative, evaluate from 1 to b This is the limit. So here we have 1 plus the limit that b approaches infinity of negative 1 over b plus the limit that b approaches infinity of 1. So this is 1 plus 1 make 2. So then we can see that here is the integral, so that the area under this curve give 2. So this will be a good estimate for the sum of the series. Yeah. So what do we know? We know that we can tell that the sum at n equal 1 to infinity, that 1 over n squared, is bounded by that curve, and this is less than 2. Okay, it's less than 2. So this series convert. So then sum at n equal 1 to infinity square is convergent. That is bounded above by 2. Suppose f is a continuous positive decreasing function on the interval 1 to infinity, and let a sub n equal f of n. So then the series converge if and only if the improper integral 1 to infinity of f of x dx is converged. Okay. In other words, the integral is converged, then the series converge. If the integral is diverge, then the series diverge. Example 1. Determine whether the series converge or diverge. The sum at n equal 1 to infinity of n divided by 3n 2 times n to the third plus 1. So let's consider the function. So let f of x equal x divided by 2x to the third plus 1. And let's calculate the integral from 1 to infinity of x over 2x to the third plus 1 dx. So this integral is less than the integral from 1 to infinity, the 1 divided by 2x squared dx. Okay, and this is 1/2 integral from 1 to infinity, the 1 over x squared dx. Well, earlier in chapter 3, recall the integral from 1 to infinity, the 1 over x to the p dx. If p is less than 1, then the integral diverges. If p is greater than or equal 1, then the integral converges. So in this case here, we're looking at a convergence, or you can go ahead and calculate this out. This is equal to 1/2 times the limit at b approaches infinity of negative 1/2, evaluate from 1 to infinity, from 1 to b. So this is 1/2 the limit at b approaches infinity, and this is negative 1 over x times negative 1 over b plus 1/2 the limit at b approaches infinity of 1. Okay. So this is equal to 1/2. So we can see that this integral here converge. This implies the sum at n equal 1 to infinity of the series n divided by 2n to the third plus 1 converge. In the next case, we have the sum at n equal 1 to infinity of 1 divided by square root of 2 minus 1. And let's talk about the convergence and divergence of that series. Let f of x be the function. Let f of x be the function (1 divided by root 2x minus 1). So then the integral from 1 to infinity of 1 divided by 2x minus 1 square root dx. This is equal to the limit at b approaches infinity, the integral from 1 to b of 1 over square root of 2x minus 1 dx. We can do a u substitution, and this becomes the limit at b approaches infinity a square root of 2x minus 1 evaluate from 1 to b. This is equal to the limit at b approaches infinity a square root of 2b minus 1 minus 1. This is equal to infinity. This meant the integral is diverged. Therefore, the sum is diverged. Remember this fact. Recall that the integral from 1 to infinity of 1 over x to p dx when p less than 1 diverge. We use that fact to calculate what is the value for p, so that the series, the sum at n equal 1 to infinity, the 1 over n to the p converge. So recall the integral from 1 to infinity, the 1 over x to the p dx. This converge if p is greater than 1, diverge if p is less than or equal to 1. So then this implies this sum here for n equal 1 to infinity of 1 over n to the p. This series is converged if p is greater than 1 and diverge if p is less than or equal to 1.